Hello, this is Erica Podest, and today's seminar will be an introduction to SAR interferometry. Our guest speaker is Dr. Eric Fielding, who's a scientist with the Earth's Surface and Interior Group at NASA's Jet Propulsion Laboratory. He has a PhD in geological sciences from Cornell University, and his current research interests include the application of SAR interferometry for measuring deformation on and around faults, before, during, and after earthquakes, and on landslides. I'll pass it over to Dr. Fielding so he can get started.
Okay, thank you, Erica, for introducing me. This is Eric Fielding. I'm a geophysicist at the Jet Propulsion Laboratory, and I'm going to be talking today about SAR interferometry, a way of analyzing pairs of SAR images to extract information about topography and or surface deformation. The objectives today are to understand the basic physics of SAR interferometry, understand what the SAR interferometric phase tells you about the land surface, and describe the data pre-processing and processing steps. And then understanding what the interferograms mean at the end. You should have already seen the two previous webinars, the Basics of Synthetic Aperture Radar and the SAR Processing and Data Analysis webinar, because I'm going to assume that you've already seen those and not cover any of that material. So, SAR interferometry theory. SAR interferometry is a way of just to give a quick review of what Erica covered in the SAR imaging tutorial. One of the things we want to remember is that there's this kind of speckly appearance that's in radar images, the SAR images, and that's because there's a number of different objects within a given radar pixel that add up to one radar measurement. And the key thing that we're going to be talking about today is that there's this addition of all these reflections off the different objects affects the phase of the radar signal. And the phase is the key thing in interferometry, because that's what we use to actually make all the measurements. So this is just showing two different pixels and how each pixel can have different phases, but the total phase is the coherent combination of all the different sub pixel scatterers. The radar phase is actually a measurement of how the total distance between the satellite radar antenna and all the objects in the radar pixel. And in fact, that the radar phase is a fraction of the radar wavelength. The radar wavelength typically is between 3 centimeters and 24 centimeters. 3 centimeters X-band, 6 centimeters C-band, and 24 centimeters for L-band. The total phase is actually a huge number of millions of cycles, because there's millions and millions of 6 centimeters between the radar antenna and the ground. But what we want to actually measure is the difference in phase between two different images. And interferometry is just a more quantitative way to say that we're going to take the difference between the phase of two radar images. So, as a very simplistic way to look at this, the phase of image 1 is we have this standard thing in all interferometry. It's the 4 pi over lambda 4 lambda being the radar wavelength. 4 pi because it would be 2 pi. 2 pi is a full circle of phase. But in this case, because the radar beam is going out and coming back, we have to multiply by 2. So it's 4 pi divided by the radar wavelength times rho, which is the distance, the total range as shown on this previous slide. So the phase that we measure in image 1 is 4 pi times rho of image 1 plus some other effects that are due to a lot of the different effects that we're going to talk about later, and then an N for noise. And then we have phase of image 2, and similarly times the actual range of image 2. And the actual total of all these constants cannot be directly determined, but because they depend on the radar imaging geometry, by taking the difference, we can subtract out almost all of these constants and get a phase difference, which is the difference in phase between the image 1 and image 2. So there's actually 2 different types of radar interferometry that can be done with radars. There's what we call cross-track interferometry, where we have 2 images in different times or different locations looking at the same point on the ground and doing interferometry in the direction away from the radar or the range or cross-track direction. This is can be used to measure topography and surface deformation. There's also a type of interferometry that they call along track interferometry, where we take, as the satellite is moving over, we take a radar image at one time, and then maybe a second later, look at the same scene from a different place along track and take the difference of that, and that can actually measure the motion of the ground surface, especially the waves of the ocean. So this is good for oceanography, and this is good for all the cross-track interferometry is for all the surface Earth surface deformation products and Earth surface land elevations. I'm only going to be talking today about cross-track interferometry and not saying anything more about along-track interferometry. These are some typical cross-track interferometry applications. With airborne systems, there's ways to make detailed topographic maps using the radar interferometry and using 2 different antennas on the same aircraft. That allows you to measure the topographic elevation to high accuracy over quite a wide swath. And it's presently being used for measuring the topographic change in volcanoes and ice sheets. And we also use this technique in the NASA shuttle radar topography mission that flew in the year 2000 to measure the topographic elevations of about 80% of the Earth's surface using the space shuttle, where we had 2 different antennas on the space shuttle to measure the topography up to latitude 60 degrees north and 60 degrees south. Then that's the topographic mapping application. Then the other major class of application is deformation mapping or detection of change. And that is done by taking 2 images at 2 different times, where we can measure the amount of elevation change or other change of the surface between the 2 times. So we can say if we have an image, radar image from the satellite before an earthquake, we can come by again after the earthquake. We can take another image and see the deformation due to the earthquake by taking an interferogram. So I'm going to go through some slides showing the geometry of SAR interferometry. I'm not going to go through all the equations in detail, but it's important to know the basics of the geometry to understand what interferometry means. This slide shows the basic geometry for measuring the elevation of the land surface, Z for elevation. We have two different antenna locations, A1 and A2. And those two, as I was mentioning with the shuttle radar topography mission, we actually had the space shuttle here at one location and a long boom, 60 meters long, with the second antenna located at the end of the boom, giving a baseline. B is for baseline here, distance of 60 meters between the antenna 1 and antenna 2. And then we can look, as I was mentioning earlier, the phase is the measurement of the range, or rho here. And we have the phase at antenna 1 and the phase at antenna 2 that has a different phase due to the difference in angle here of the triangles. And the difference in phase between these two radar measurements is proportional to the elevation, as shown in this equation here. The elevation is h, the height of the satellite, minus the range to the ground, times the cosine of the angle here between the satellites. And we know the baseline distance. We measure that very accurately with the space shuttle. We actually had a whole detailed metrology system that used lasers to measure the length of the boom in case it changed during the flight as the boom went in and out of the sun. And we also have to measure the angle that the baseline makes, which with the space shuttle, we had a whole detailed measurement system to measure that angle. Once we know that angle, then we can convert the difference in phase between the two satellites to make an interferogram. This is just showing that there's actually two different ways to operate the imaging systems. With the space shuttle, we had only one big antenna that transmitted. So we did what they call this classic mode, where we transmitted the signal from the main antenna, and then the signal came back to antenna 1 and to antenna 2. That's using this equation. There are some other systems, like the German Space Agency had two different radar satellites where they could actually have the two antennas separate on two different satellites and do a different acquisition mode they call ping pong, which just changes the phase by a factor of 2 here. The second option, as I was mentioning earlier, if you want to do deformation measurements, then you can collect data in what we call repeat pass mode. In this case, we make two measurements at roughly the same location, but at two different times. In this case, we still need to know the baseline or distance between the two radar antenna locations, but it's more difficult to measure because we need to know the orbits of the satellite or space shuttle or whatever, and then be able to take the difference between those. And this then allows us to measure deformation that happened between the two acquisitions. And so this is just showing an example of how the phase of ground deformation, we have our two antennas up here. We have at time t1, the range or distance of the ground is rho t1. And at time t2, the antenna is almost the same location, but the ground is moved due to an earthquake or something like that. So then we have a rho t2, and if we take the difference, then we have a delta rho due to the ground deformation. And if we have this same magical 4 pi over lambda multiplied times that delta range change, or delta rho, we get the change in phase. And the change in phase is what we measure with the interferograms. And this picture on the right here is an example of a interferogram of an earthquake that happened in 1999 here in Southern California, called the Hector Mine earthquake. It's generally a little bit more complicated for satellite systems because we can't get the second antenna back to exactly the same location. So then we have a mixture of the phase change due to the ground motion and the phase change due to the baseline between the two antenna locations. So in this case, then we have the range at time t1 from this antenna location, and then we have at a different time the antenna comes back to a different location, has a distance of b, and then we have a range at time t2. So now our phase that we measure from the interferometer is a combination of a term that's due to the topography, any elevation of the surface, and the term that's due to the ground deformation. So we actually have to find a way to separate those two. And in general, we know what the topography is. So if we look at this equation down here, we can estimate. If we know what the height of the topography is, ht, and we know what the baseline is, we actually have to convert it to the, or it's called the perpendicular baseline. It's just the baseline, the component of the baseline that's perpendicular to the look direction. That's the part that determines what the sensitivity is to elevation. If we know and we know what the distance is, then we can calculate this whole term using the digital elevation model, and then get the range change that's due to the ground deformation. And important thing to know is that the sensitivity is very different for elevations and for displacements. And that's because of the elevation is the phase change that we measure. This is taking the derivative of phase change relative to a change in height. And for a given height change, the amount of phase change is dependent on the range. Here, the range rho and times the lambda, and this angle here is just the perpendicular component, and the b is the baseline. So unless the baseline is very large, then the phase difference here is quite small. And as it's written down here, in almost always you always have to have the baseline b be much smaller than the total range. Say for the space shuttle, we had the baseline of 60 meters, and the total range to the ground was around 400 kilometers. So that's a very big difference. So that means that the sensitivity to 1 meter of height change is quite small. Whereas the sensitivity to displacements of the ground surface is simply 4 pi over lambda. That means for 1 meter of ground motion, we'll see a much bigger amount of phase change than we would see for 1 meter of elevation change. So this is just writing that in terms of sigmas or error estimates. So the errors in displacement measurements are the displacement sensitivity is much greater than the topographic sensitivity. So we can measure topography at the scale of meters. The estimated accuracy for the shuttle radar topography mission was around 10 meters, whereas we can measure topographic change or surface displacements on the order of millimeters. With C-band radar, just a few millimeters; with L-band radar, around 5 millimeters. Much smaller than the meter scale or tens of meters scale accuracy of topographic measurements. So one of the other key issues in making interferometric measurements is that we would like to have the phase difference, the actual phase difference here. But in the nature of interferometry, we can only measure phase modulo 2 pi, or 1 cycle of phase. It's basically, it goes around a circle, and we can only measure where it is on the circle and not how many times it's gone around the circle. So and on this line, we show what the original phase is, because we can only measure how many cycles. Well, we cannot measure how many cycles of phase there are. We have to use a special measurement technique we call phase unwrapping, because the phase measurements that we can make with the interferogram are only between, say, pi and minus pi and pi, and that means that the actual phase ends up with these discontinuities where it goes from minus pi to pi. So this is what we measure with the interferometer, and we have to use computer programs to go through the step of trying to figure out where these discontinuities are and what sections need to be moved back up to connect and get back the original unwrapped phase. So this is a little bit of a complicated part of interferometry, but it's a key part of actually doing interferometry. So there's one more aspect of SAR interferometry that's a key aspect to know about. So far, we've been talking about the phase of interferograms. There's another part of the measurement that's called the correlation, and this is or coherence. Some people use coherence, other people use correlation. Usually, you'll see correlation. This is a key aspect of SAR interferometry, and it's basically how noisy the data, each area of the interferogram is. And INSAR signals can be decorrelated or become incoherent due to a number of effects. Generally, it's due to changes on the ground, which is the category here of random motions over time. If the things that were reflecting the radar on the ground change drastically, then that pixel will become incoherent, and the phase will be randomized and become pure noise. And correlation is actually a way of measuring, estimating what that coherence is, because we can't actually measure the coherence directly. And so that's why we call it correlation. And the opposite of correlation is decorrelation, when something becomes incoherent. And if something is decorrelated, that affects the measurements of either height or displacements, and it also affects the unwrapping of phase. Another important thing with the correlation is that the correlation components multiply, unlike the phase effects. Yeah, you may remember earlier we talked about the topographic phase and the ground displacement phase. Those two effects are added, but correlation effects are multiplied. That means that if any one of these effects is low, then it causes local correlation for that area and complete loss of information. So that's a key thing in SAR theory that you'll see in the literature. So now I'd like to talk about some applications of SAR interferometry. We'll be just giving a quick overview of some mainly solid Earth applications. There's these examples of deformation on one page. The key examples are the top left corner earthquake, the top right corner a volcano, bottom right corner a velocity of ice streams, and in here in the center ground subsidence. I'll be talking a little bit more about each one of these subjects. These are some examples of deformation that were detected in volcanoes of the Andes some years ago by Matt Pritchard, who's now at Cornell. He found that many of the active volcanoes had some deformation going on, and some areas that were not known to be active also had deformation. So ongoing efforts to understand what's going on with the volcanoes in the Andes. This is an example of a large dike injection. Sometimes magma from the deep in the earth comes up and opens a fault or dike in the surface and causes a huge amount of strain. In this particular case, this area in central Ethiopia opened up by about 2 meters. All these fringes here, each one of those 3 centimeters fringes shows that the ground was expanded here by about 2 meters in 2005. Another big area of use of INSAR is earthquakes. This is one of my main topics of research. This is an interferogram of a large earthquake that happened in 2015 in magnitude 7.8 in Nepal. It's called the Gorka earthquake. This is an interferogram from the Japanese satellite ALOS-2, and it's a special mode they have of called ScanSAR that images a very wide 350 kilometer wide swath. And in this particular case, the radar line of sight is to the right, and the earthquake motion is almost perfectly parallel to the satellite track. So the line of sight is only picking up the vertical motion. We can see that this area in blue up here in the high Himalayas dropped down by as much as 1.2 meters, and areas to the south, including Kathmandu, were uplifted by up to 1.6 meters. Another thing we can look at is slower earthquakes or aseismic creep. This is an example from the central San Andreas Fault, just showing how the fault has moved over the course of 9 years using ERS interferograms. As I mentioned earlier, groundwater withdrawal can cause rapid subsidence. This is an example from the city of Las Vegas in Nevada, and rapid subsidence in Nevada due to pulling groundwater out of the ground. This is another image showing velocities of ice streams in Antarctica. This is actually a combination of SAR interferometry and another method called feature tracking, which we didn't cover in this introduction, but it's a way of measuring large motions. And this is an example of detecting ground motions that are due to oil enhanced oil recovery in Argentina, done by Matt Pritchard in using MVSAT data. As I mentioned earlier, correlation is actually one of the parts of the INSAR measurements, and we discovered back when the 2003 earthquake, magnitude 6.5, destroyed the city of Bam in Iran. We looked at the correlation image and we noticed this line of low correlation extending south from the city, and sent this image to colleagues in Iran, and they were able to map the surface ruptures in the field by using the correlation image. These little circles here show where they map the surface ruptures in the field. And we also noticed that we could actually detect both the surface ruptures and the damage to the city by looking at the change in correlation. This is a correlation change image from taking the coseismic correlation and subtracting the pre-seismic correlation image. And the red here shows where the correlation decreased. This area to the south is where that surface ruptures are located. And these areas of large correlation change within the city of Bam show where there were huge amounts of destruction to buildings in the city. Unfortunately, at least more than 20,000 people were killed in this earthquake. And this has now been turned into what we call a damage proxy map for detecting damage from earthquakes and other effects by using the INSAR correlation change as a measurement of how much the surface changed. And that just shows how the fault rupture to the north directly into the city led to this large damage. We also look at landslide motion. This is a combined product from 4 NASA UAV SAR flight lines over a landslide in Colorado. And we are actually able to construct the full 3-dimensional ground deformation and see how the landslide is moving relative to the surrounding rock. So that's a quick introduction to some NASA, some applications. Erica showed this slide before. I just wanted to repeat it about the NASA ISRO SAR mission that's going to be launched in late 2021. And there's more information about INSAR applications at the NISAR website, nisar.jpl.nasa.gov. So now we're going to move on to the demonstration part of the webinar. So the next step we want to look at is getting radar data. The NASA site that has radar data is the Alaska Satellite Facility, and they have a number of different satellite images from different satellites, including the European satellite ERS. There were 2 ERS satellites, ERS-1 and ERS-2, that operated between 1992 and 2012, over just about 20 years of data. And then there was the MVSAT satellite. That data is not available from the Alaska Satellite Facility. There's data from the Japanese satellite, ALOS, that operated between 2006 and 2011. And the new data sets from the European Space Agency, the Copernicus Sentinel-1 radar products, which we're going to talk about today. So the Alaska Satellite Facility is now getting a complete copy of all the Sentinel-1 data that's acquired by the European Space Agency. They get it with a little bit of delay, so if you need the latest images, you may need to go to the European Space Agency, but for data that's more than, say, a few days old, the Alaska Satellite Facility, ASF, should have almost all the data. And we go to their data search site. I just pressed this Find Sentinel-1 Data button. It comes up with this search interface they call Vertex. This is the main way to search for radar data. And for the demonstration I'm going to do today, I'm going to search for the radar data for an earthquake that happened in South America, in Chile, back in August of 2015. It was called it was a magnitude 8.3 earthquake, and it was near the city of Illapel in Chile. So seismologists call it the Illapel earthquake of 2015. So we've gone into the Vertex software interface for the graphical user interface for searching for the Alaska Satellite Facility radar data. I'm going to enter in the area that I want to cover. It's between 72 degrees west and 71 degrees west, 30 degrees south and 32 degrees south. I know that the dates of this earthquake are spanned by 2015, 08, 24th of August, and the 2015, 9, 09, 19, the 19th of September. Under data sets, well, it's set to Sentinel-1A and 1B. Sentinel-1B wasn't launched until 2016, but it doesn't hurt to leave it in the list. And for this particular demo, I know that I want to get data from path 156. I'm just going to enter that in to avoid getting too many results. But you could not set that and see more data. And it immediately found the scenes. Here in the middle, we see the map of which scenes cover this area. That Sentinel-1, this is a descending track where the satellite is moving southward. So as it goes southward, it goes further west. That's how we know it's descending. And the Sentinel-1 data is divided up into frames or slices, and it takes 3 of these slices to cover the area that I requested. And then over here on the right, there's now a list of the scenes of those slices or frames. There's 3 for each date. So date September 17th, there's frame 701, frame 696, and frame 691. Well, they go southward as with the numbering. For this particular demonstration, we're going to look at frame 701, which covers the city of Santiago in Chile. So we want to download path 156, frame 701 from September 17th, 2015. You notice that the granules have this long name that Erica explained in her demonstration. But whereas Erica asked you to download this high-resolution single polar, high-resolution detected product, the GRD-H product, for interferometry, we have to use these what they call single-look complex products, SLCs. And these are generally quite a bit bigger. So in this case, it's 2 gigabytes. I'm going to press download now, but it's going to take a while, so we won't wait for that to download. You have to log in to be able to download the data. I've already logged in earlier, so it didn't ask me to log in again. But if you're doing this for the first time, since you open your browser, then the ASF will send you to the Earth Data NASA Earth data site where you have to log in before it'll allow you to start downloading the data. Then we're going to do the same thing for the other date. Interferometry requires the two dates. We have to make sure we get the same frame. This is frame 701, again from the same path and same frame, so we always have to have the same frame and same path in order to do interferometry. But this is the acquisition date of the August 24th scene. So again, I'm going to download the SLC product down here, and I'm not going to wait for that to complete. We'll go on to the rest of the processing while that's running. Okay, so the next step is to, after we've downloaded the data, is to use the Sentinel-1 toolbox. So the Sentinel-1 or SNAP program. I've already started the program. You'll have to find it on your computer and start the program. And then first step is to open the product. You may have to find where your product is on your computer. Mine's here in this EFL S1 directory. The downloaded images are in these zip files, as Erica explained in her tutorial. And you don't want to unzip the file because the toolbox reads the zip file directly. So I'm going to select this one. This is the August 24th scene, and open it. In this case, it says it's already open. I don't really want to open it again. I already have this open here as image number 1 in my Product Explorer. And then you'll see that there's a number of different pieces. Erica mentioned some of these other pieces before about the metadata and tie point grids. The SLC data products have somewhat different format. They're all in radar coordinates rather than in geocoded coordinates. They also come with what is called a quick look image here. If we click on the quick look image, it'll show you an overview of the whole scene here. The Sentinel-1 interferometric wide swath mode that we use for interferometry has 3 subswaths, and you can see these sort of stair-stepping appearance of the radar image because of each subswath stops and starts in a different location. And then if you look at the bands part of the Product Explorer, you'll see that in fact it's showing the 3 subswaths as separate images. This is if we click on image IW1, that's image number 1. This is the part of the subswath on the left of the. Note that all of these images are in radar coordinates. In radar coordinates, the left side of the image is closest to the satellite. The satellite is moving south and looking to the west. So the side of the image that's closest to the satellite is actually the east side. So all of these are flipped east-west relative to what you are used to looking at, and that's why the ocean is on the right side of the image and the land is on the left side of the image, even though this is the west coast of Chile. And this bright spot here is the city of Santiago. We can see that here in the radar image. The actual Sentinel-1 TOPS mode interferometric wide swath images are made up of a whole bunch of separate bursts. This overview quick look image doesn't show the bursts, but if you look carefully, you'll see these little cuts in the image on the intensity images, which are the cuts between the bursts. This is subswath 1, IW1. This is subswath 2. This includes the coastline, and this is the one that we're going to process for the interferometry. And then subswath 3 in this particular scene is all water, and that's not worth looking at this point. So then I also opened the second scene, which is the September 17th scene. And if we look at that, we should Here is subswath 2 of scene number 2. It should look the same. If we're going to do interferometry, we need 2 images that cover the same area, so they should look the same. So that's the first step of getting ready to do interferometry, is opening the 2 data files and verifying that the 2 frames or slices or scenes that you've downloaded are the same area. So then the first step of doing SAR interferometry is to co-register the 2 SLC images so that we can do this phase differencing. So the Sentinel-1 toolbox has this special radar co-registration, Sentinel-1 TOPS co-registration, Sentinel-1 TOPS co-registration. We get into here for this. It comes up with this dialog box. It may look a little different. I'm on a Mac. On Windows, it looks a little bit different. We want the first scene to be the August 24th scene. So under read, we set it to the August 24th scene. And then read 2 is the second scene, and that's the September 19th scene that we just opened. Then we can only process the interferometry for one of the subswaths at a time. So this next tab here is where we tell it which subswath we want to process. In this case, we want to process subswath 2, IW2. We're going to process all the bursts. And in this case, this data only has 1 polarization, so we don't choose a polarization. We have to set subswath 2 again for the second scene. Under the next tab is just telling it to go ahead and contact the Sentinel servers and download the orbit data it needs. Also for both for the second scene, the next tab is it's going to automatically download the shuttle radar topography 3 arcsecond digital terrain models, and it'll automatically go out and do that. And it's going to mask out the area of no elevation, which is the ocean. You don't need to change that. You can use the 1 arcsecond DEMs if it takes a little bit longer to process. So in this case, we're going to just use the 3 arcseconds. That's the spacing. 3 arcseconds is 90 meters on the ground. 1 arcsecond is 30 meters on the ground. And then the output product is automatically, the name is generated from the master scene, or the first scene that was selected. So it's that whole scene name with orb stack here at the end. Now I've already, at this point, I would just press run. This process takes about 5 or 6 minutes, so I'm not going to wait for this to finish. That's getting set up for doing the TOPS co-registration. And just like on a cooking show, I'm going to come back and show you that the stack is already here. I actually did both the subswath 1 stack here and the subswath 2 stack. Subswath 2 is what we're going to be looking at today. The subswath 1 is largely incoherent because of the the snow in the Andes Mountains. So this is the output of that co-registration step, is what they call an SLC stack, an orbit stack. Now, if we look at the bands that are available, there's an intensity for the August 24th scene, and there's an intensity for the September 17th scene. And these 2 images are now precisely co-registered. One of the things to notice is that these are complex images still. The I and Q here are just the two, the imaginary and real components of the complex numbers, but they have this option of displaying the intensity image, which is just the square of the complex number. And it has a V here because it's actually a virtual image. It's not actually saved in the file. It's calculated on the fly. So the next step, now that we have our two single look complex images precisely co-registered, is to make an interferogram. And I started showing what it looked like after it's done. Let's show how to make it first. So we go back under the radar menu under interferometric, products, interferogram formation. So the interferogram formation takes the source is this is the beam subswath 2 orbital orbit stack, which has the two co-registered SLCs. I've selected that, and then it's going to write the output the same name with I of G added to the end. Again, you might need to change your directory here if you want to make sure it goes to the right place. Under processing parameters, we wanted to subtract what's called the flat Earth phase. That's the phase due to the difference in the orbit positions, but it's not going to subtract the topographic phase, which we'll do later. It's also going to include coherence estimation. And again, we can press run here, but it's going to take around 5 or 6 minutes to run, so I'm not going to press the run button, but I'm going to go directly to showing the results. And the results are here. My image number 9. It's the stack, and the quick look here is showing a very quick version of the interferogram phase. Now, if we look at the results, we still have this I and Q because the interferogram is still a complex interferogram. It's what we call the wrapped interferogram, but they also provide the these virtual images, one for the intensity, which is the average of the two intensities. It's mostly showing some bright spots, but that's not important. We also look at the phase. Now this phase includes both the ground deformation phase and the phase due to the baseline between the two orbits and topography. So in fact, there's some information here, but it's a mixture of that topographic phase and the surface deformation phase that I explained earlier in the theory. So now we need to go through and calculate and subtract out that topographic phase. So the next step. The other thing is that this interferogram is still the original bursts. If we zoom in here, we can see that there's these little lines between the bursts. There's 9 bursts here. So these little lines are where it goes from one burst to the next. So for the rest of the processing, what we're going to do is combine these bursts into one continuous image. These first steps have to be done on the individual bursts, but the rest of the steps can be done on what they call the debursted or mosaic image. So the next step is to do the debursting. We go to Sentinel-1 tops. This is another module, under radar, Sentinel-1 tops, S1 tops deburst. And that just takes the input being the interferogram, and the output is just the interferogram with DEB at the end, meaning it's been debursted. Again, this takes some minutes to run, so I'm going to skip the run step and just show you the results. And that's here, number 10, the debursted interferogram. The phase still looks pretty similar, but now there's not any gaps between the bursts anymore because the bursts have been mosaicked together. So the next step is to do what is often called differential interferometry by calculating the phase that's due to the topography. We use that, it's going to use that shuttle radar topography mission digital elevation model. We go in here under interferometric products, topographic phase removal, and it takes the output of the debursting, the underscore DEB file. The processing parameters is just specifying what DEM we're going to use, and it's going to write out the topographic phase here as another band of the output image. And again, this takes some time to run, so I'm going to skip ahead to the pull the cake out of the oven and go to the SAR image. And that's this one. Now, if we look at the phase, we can start to see here what the actual deformation due to the earthquake. All these fringes up here at the top of the image are the deformation due to this magnitude 8 earthquake. Fortunately, the city of Santiago is down here near the bottom of the image, and it was not severely affected by the earthquake. They are ready for earthquakes in Chile, so they didn't have much damage, even though this was a magnitude 8.3 earthquake, because they're ready for even large earthquakes there. And then you'll notice that the interferogram is still very noisy. If we zoom in, there's just a lot of speckle in the phase. That's similar to the speckle in the radar amplitude images. And we can do filtering to make the phase easier to see. And so the next step in the radar interferometric processing is filtering, interferometric filtering, and we're going to use the Goldstein phase filtering. This is a phase filter that was developed by Richard Dick Goldstein, who was a radar scientist at JPL, who's now retired. Still comes in once in a while. I think he's like 85 now. This is very, again, takes the input of the SAR image, and the output will be the same thing with a FLT for filtering. Processing parameters, you can read his paper. That's Goldstein and Warner, 1993. I will put that in the notes, the exact reference. But the key thing is that there's a filter exponent. In this case, the default for that filter exponent is 1.0. If you want more filtering, you can make this a higher number. If you want less filtering, you can make it a lower number. And that's the default. Again, this takes some minutes to run. So I'm going to skip ahead to show you the results of the filtered interferogram. And filtered phase now looks much cleaner. And in fact, for most types of processing, we always use the filtered phase. I had a little glitch with my Snap program, so I had to it crashed on me and restarted. So now the numbering is different. The final filtered interferogram, the dot or interferogram debursted DNSAR topographically corrected filtered interferogram is now number 3, but it's the same interferogram that we were doing earlier. It just has a different number and now we can see the detail in the interferogram. Whoops, I went way too far. Sometimes you have to quit the program and restart it because it runs out of memory or something. But so you may end up with your the numbering of your input images here are different, but they're still the same. It saves each stage of the as a file. It's a little bit tricky to control this zoom program. It keeps zooming in as long as you hold on to the button. I don't have time to go through all the interpretation of radar images. We can drag this around and see the different parts of the image. There's a lot more fringes up here near the top of the image because we're getting closer to where the earthquake was. Down here near the bottom, there's almost no fringes, which means that there's very little deformation. So by analyzing this interferogram, to do a full analysis, we actually had to process the next frame and the frame after that to get the whole earthquake. This is a magnitude 8.3 earthquake, so the area affected by the earthquake is around 300 kilometers long. Each one of these frames is only around 100 kilometers or 150 kilometers. So we need 3 of them to cover the whole area of the earthquake, and we're only showing 1 in this demonstration. But so this is an example of using interferometry to study an earthquake. There's some additional software that's necessary to do the phase unwrapping step. That doesn't come with the Sentinel-1 toolbox. There's a snafu program that was written by a PhD student at Stanford, Curtis Chen. Was published, his paper, Chen and Zebker, was 2002. That software is available from Stanford for a free download. You have to compile it, and on the ESA website, they explain how to run that as a virtual machine if you have Windows. On the Mac and on the Linux, you can run it directly, compile it and run it on your computer. I'm not going to cover phase unwrapping in this particular tutorial, but that's a key part of the processing. This is an example of analyzing data from an earthquake. As I mentioned earlier, this is a wrapped interferogram. Each one of these fringes is 4 pi divided by the wavelength times the surface deformation. So the wavelength of the Sentinel-1 satellite is about 6 centimeters. We divide by 4 pi. Actually, divide by 2 pi just for the circle. And so to do, we know that we should each one of these interferometric fringes is 3 centimeters, or half of the radar wavelength, due to that factor of 2 of the phase, the radar wave going to the ground and coming back. So if we can just count these fringes to get a rough idea of how much deformation we're talking about here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the same blue color here is on here 10 times. 10 times 3 centimeters means that there's roughly that there's 30 centimeters of deformation measured by this, caused by this earthquake over this distance. And that's deformation in the radar line of sight. Didn't explain in a lot of detail, but the interferometric measurements are in the range direction. I remember we're only measuring the difference in the range to the ground, so we can only measure the component of the surface motion that's parallel to that range direction. So this is why people always talk about the line of sight. That's the range direction of the radar, and all of the interferometric measurements are changes in that radar line of sight. In this particular earthquake, the ground motion was almost due west, which means that it was almost parallel to the radar line of sight, and that's why we're seeing a large amount of deformation here. These interferometric measurements could also be used to measure other things, as I explained earlier in the applications, to groundwater withdrawal, oil field monitoring, subsidence due to other processes like tunneling, can measure ice motion, motion of landslides, many different things that move on the earth. As long as the ground moves as a block over with a size that's coherent, we can measure that ground motion using interferometry. And it works great for earthquakes, especially in places like Chile, where there's not too many trees in central and northern Chile. So today, I think we've covered a lot of things, and this is an introduction to SAR interferometry. You may not be an expert yet, but at least you have some idea of what these fancy colored fringes mean, and an idea of what this means for the interpretation of interferometric products. Thank you.